Hello everyone. Welcome back to Dr. Liu's VCE Physics channel. Today, let's learn together about the 2025 NHT Physics examination. We will focus on questions related to light as a particle. My explanations may not be perfect. If any teachers, parents, or classmates find errors, please feel free to provide your guidance. Increasing the accelerating voltage by a factor of 100 directly increases the electron's kinetic energy by the same factor. Because kinetic energy is proportional to the square of velocity, the electron's speed increases by a factor of 10. Consequently, since the de Broglie wavelength is inversely proportional to momentum, the resulting wavelength is reduced to 1/10 of its original value. The correct answer is A. No photoelectric emission would occur. Because h and c are constants, the energy E is inversely proportional to the wavelength. When the wavelength increases, from 500 nanometers to 600 nanometers, the denominator in the equation gets larger, which makes the total energy E smaller. Since the 500 nanometers light was the threshold exactly enough energy to eject an electron, any energy value smaller than that will fail to cause emission. To solve this question, we need to calculate the wavelength of a laser that provides exactly the right amount of energy to move an electron between two specific energy levels in a hydrogen atom. First, determine the energy difference. According to Figure 16, the electron moves from the ground state, n equals 1, to the first excited level, n equals 2. The energy required is, then, direct wavelength calculation. Using the value of h and c, we can solve for wavelength directly in nanometers, substituting our values. According to the de Broglie relation, the momentum of a photon is inversely proportional to its wavelength. By substituting the laser's wavelength of 103 nanometers and Planck's constant into this equation, we determine that the momentum of the photon is approximately. An electron in the n equals 3 level can return to the ground state via 3 distinct downward transitions. It may transition directly from n equals 3 to n equals 1, or it may decay incrementally from n equals 3 to n equals 2, and subsequently from n equals 2 to n equals 1. Each of these three transitions corresponds to the emission of a photon with an energy equal to the difference between the two specific levels. The photoelectric effect experiment distinguishes the particle model of light from the wave model of light. The following observations are made in a photoelectric effect experiment. Observation 1. The kinetic energy of the electrons emitted depends on the type of metal surface involved. Observation 2. For a particular frequency, the number of electrons emitted from a given metal depends on the intensity of the incident light. Observation 3. The kinetic energy of the electrons emitted from a given metal depends only on the frequency of the incident light. The wave model cannot explain observation 3. The kinetic energy of the electrons emitted from a given metal depends only on the frequency of the incident light. Particle model. Light consists of discrete photons where E equals hf. One electron absorbs one photon. Success, increasing frequency, f, directly increases the energy of individual photons, thus increasing the electron's kinetic energy. Wave model. Light is a continuous wave where energy is determined by intensity, amplitude, not frequency. Failure. It predicts that higher intensity light, regardless of frequency, should provide more energy to ejected electrons. While the wave model fails observation 3, it can explain observation 2 because higher intensity, in either model, means more total energy is hitting the surface per second, which logically results in a higher number of electrons being emitted. Observation 1 is not a deciding factor between the two models because both theories agree on the nature of the metal itself. Wave model. It views the metal as having a grip binding energy that varies by surface type. Particle model. It views the metal as having a specific work function, the minimum energy a single photon must provide to liberate an electron. Because both models correctly predict that the surface material influences the final energy of the electron, observation 1 cannot be used to prove light is a particle. Only the frequency dependence, observation 3, acts as the smoking gun that proves the wave model is insufficient. Photoelectric effect, wave versus particle model. Kinetic energy depends on the metal type. Both models can explain it. Both models recognize that different metals have different binding energies or work functions that must be overcome. Number of electrons depends on light intensity. Both models can explain it. Wave, higher intensity means more total energy delivered. Particle, higher intensity means a greater number of photons. Kinetic energy depends only on frequency. Wave model cannot explain it, but particle model can. Wave predicts intensity, not frequency, should control energy. Particle energy is tied to frequency via E equals hf. Particle nature of light. Light consists of photons with energy and momentum. Photon energy depends on frequency, not intensity. Broglie wavelength matter has wave properties, increasing accelerating voltage speed and momentum wavelength. Photoelectric effect. Threshold frequency required for emission. Electron kinetic energy depends only on frequency. Light intensity controls number of electrons, not their energy. Atomic transitions, hydrogen, photons absorbed or emitted when electrons change energy levels. Energy difference determines photon wavelength. Multiple emission pathways possible. Wave versus particle models. Both explain intensity effects and metal dependence. Only particle model explains frequency-dependent electron energy. Photoelectric effect is key evidence for particle model. Should you require assistance, please feel free to connect via WeChat or WhatsApp and send an email. Thank you for your attention. Kindly note the details of Dr. Liu's VCE Physics, Chemistry, and Biology channels.